Hi guys, how's it going? So today actually we're going to be going through machine learning systems lab. So we're going to be predicting real names based on nicknames. So I thought this will be a cool project, especially to try to understand some of the concept in natural language processing. So the first thing that we're going to do is that we'll try to understand the requirements. We try to understand if the data that we have, it is labeled. We'll try to understand if the production system that we're going to build, is it going to be used in production in real time, or it's going to be a batch system. We're going to try to understand if the nicknames that we have to predict, do they have a pattern? Is the pattern that we can leverage, right? We'll try to understand if this data is labeled, do we have an existing data, or we have to label from scratch. We're going to look at how we can collect the data and what are some of the techniques that we will use to collect this data. Some of the data that we're going to collect is not clean, so we need to make sure that the data that we collect it's clean, meaning that it's quality data. So we're going to look at those techniques that we can leverage. So we're going to look at those types, and we're going to look at how we can go about labeling this data. We're going to look at some of the techniques in the industry that are being used today. We're going to create features based on certain assumptions. So these features are going to help us to actually be able to map these real names to nicknames. We're going to get into modeling. We're going to look at different modeling techniques that we can leverage, which are going to help us to build this. We're going to look at compare these type of models, and we're going to see which one could work better for us. We're going to compare different types of embeddings of these weights, and we're going to look at things like subweights, our character level embedding, and we're going to go into too much detail. We're going to close this by looking at other techniques that we did not leverage and that could have had a good impact into the system. So with that said, let's get into it. The question states that how do we map nicknames to their real names, right? So the first thing that I'm gonna clarify will be that, okay, is the data labeled? If we have Rob, do we have like Robert, right? So the reason I'm asking this is because this is going to shape if this problem might be supervised or unsupervised. However, it should be noted that even if this data is labeled, however, it should not literally limit you from exploring different techniques. So you can still leverage other techniques even if the data is labeled. So my second question will be, I want to know if we're given a real name, do we want to associate nickname only one accurate nickname, or we just want like multiple of them? So my point with this question is to know if this question is going to be a multi-label task, or it's going to be like given a real name, you just want like only one thing. So this is going to be a multi-label task, meaning that if you're given a real name, you just return, or you're given a nickname, you just return multiple nicknames, something like that, right? My second question will be more of an MLOps question, which is that I want to know if this will be used in production or in a batch mode. So for me personally, I thought this what can be used in production. By the way, guys, this question I think was asked by Facebook. So my thinking was that maybe they can use it in like some sort of like a chat conversation. For instance, let's say a user account, maybe their nickname is Robert, and maybe someone texts them and tell them Rob, and you want to, and this might be in a group conversation, and you just want to know who's Robert is, and man, who's Rob, right? So you might want to associate this text to this account, something like that. That was just my use case. Maybe it does not make sense, but that's how I think it might be used in production. So the second clarification that we're going to look at is that how should we map nicknames, right? Because my thinking is that, for example, like William and Will, there's a pattern. You can see that there's a Will here, right? This is a pattern that we can leverage. Messi, nickname, they call him Pal or La Palquita, something like that, right? But here there is no pattern. I don't know like what the pattern will be. And Ronaldo, on social media, I call him gold. And literally here, also, there will be no pattern. So my point asking this question is that, does the interviewer want me to map even the nicknames that do not have a pattern, which according to me, it can be quite difficult, mainly because it's like taking a name out of nowhere and just mapping it to, to somebody else or something like that. But if that's something they want, we can also leverage that. We can also come up with technique to achieve something like that. The second thing, which is quite important, data labeling. So my question will be, do we have a labeled data? If yes, and if we don't have a labeled data, we have to come up with like some ways we can actually collect this data, and we need to find ways in which we can actually be able to clean this data that we've collected. So this is a real world use case. Based on like reading so many use cases, I can tell you that for the most part, data is not labeled, and you have to find some techniques to label it, and that's why we're going to talk about that in more detail as we go on. So data collection. The first thing, because like I said, this was asked by Facebook, and if I go to Facebook, as you are looking at this image, you can see that there's a name, and if you go under detail about, you'll see that there is other names. So I am thinking that this could be our first data collection source. This could be our source, whereby we go to each account, right, and we go to their other names, and we try to see if like we can find like nicknames. But also, like, Wikipedia is very, very, very powerful source, so we can leverage Wikipedia to extract nicknames that have been mapped to real name, right? But the problem with this is that it's not a clean data because it's generated by an automated means, meaning that it won't be accurate as much we might want. So the question is, how then do we get this data to be accurate? One way we can maximize data quality by applying some techniques in computer science. So one technique is called lowest common subsequence. So it's a dynamic, I think it's one of the dynamic programming lead code questions. But the point here is that if you're given a name like this, sorry guys, actually let me zoom in so that you can see. So now you can go to Facebook. What happened is that users can be able to link other names. So this could be possibly be our source, because we have probably maybe this is a nickname or a real name, we don't know, but we can try to map that to this, right? That's one way. That's like me thinking out of the box, how we can try to come up with like the data. One way we can come up with the data is that we can leverage Wikipedia. So Wikipedia, there's a lot of data whereby they link our nickname to their real name. However, this technique does not actually guarantee us that we're going to get quality data, right? So we need to maximize quality data because this is quite important. So how can we do that? So we're going to leverage some of the computer science techniques, such as lowest common subsequence. This is a programming challenge. I think it's a dynamic programming challenge on LeetCode. You can check this question out. But essentially the point is that if we're given a real name and a real a nickname, we want to see what weight in a sequence matches, what characters match in the sequence. For example, we have A here, and we have A here, we have A here. So that's one. We have B. Do you have B? Yes, we have B. That's two. Do you have C? Yes, we have C. That's three. Do you have D? Yes, we have D. That's four. Do you have X? No, we don't have X. This, it's behind. So we're moving forward. So that's why we're only considering the one that forward. So here, it will be 4. So why am I doing this? I'm doing this because all the data that we're going to collect, we're probably going to have to run it through this algorithm so that we can make sure that we want whereby maybe we have a higher score of like LCS, right? This is going to make sure that at least we have like nicknames that have some sort of like a pattern. However, this algorithm is not cheap. It's quite expensive. The time and space cost us M and N, M denoting the first maybe real name, and N denoting a nickname. So that's that. So are there other techniques that we can leverage? So yeah, we can. There's some more complex techniques that we can leverage, which is also fuzzy string matching algorithms. So fuzzy matching strings algorithms, in the background, they're using some of the computer science algorithms like Levinstein's distance, which is also a string metric for measuring difference between two sequences. So we also have techniques such as Hamming distance. So it also measure a distance between two strings of equal length. And the problem with this one is that Hamming distance is that if you have something like padding, it might not work. So what I'm saying here is that, for instance, let's say you have this nickname here, Caroline, right? You have Catherine. So what it does is that it will say, okay, cool. What are the things that do not match? Okay, Caroline, this three, and what is it? THR. They do not match. So we have KARIN, KARN. So three words do not match. So these three, they do not match. But the problem is this, is that, as you can realize, when we don't have the same sequence of words, so let's say we had like Caroline and we had something like Kath, ne? What will this do is that you need to pad it at the beginning, but then this might not give you the accurate results if you pad it. So that's like the best side of this. So hence, like, that means you still need to take all the names and you need to pad them, which can add another computation, since we can see that also the time complexity of this is of n, but the thing is, it's expensive because you still need to pad this, and it's not actually accurate compared to other techniques. So Levinstein's distance, it also has the same time complexity as lowest common subsequence. I think it's O of mn time. So I'd like to kind of like walk you through an example to how these metrics work. So so let's just do this. I'm just gonna try to zoom in. So let's say here we have Hector, right? And we have, maybe I'm just gonna write Hector with E here, and I'm gonna run this, and you can see that I'm getting 83. So there's quite a match between these two words. But if I'm writing something like Garabo, there is no match. You see, the score is very low, 70. So this is how these algorithms works, and they're using those algorithms that we spoke about in the background. So one way, because given that we have a lot of billions of names, I'm assuming, maybe I might be wrong, but you might be thinking from different languages. But yeah, we can use PySpark, whereby we're creating a UDF. I know that a lot of people don't like UDF. They say that it's very slow, especially in production. But my point is that what you can do is that you can create this function, and you can create a data. You can create you can take a data frame, and you can take a real name, and you can take the nickname. Then you run a similarity score. Then what you do is that you filter similarity score that has a high score, and you apply this function across this. So I'm thinking if you're probably using something like Spark, whereby data is distributed in on different clusters where the computation is taking place, you can do something like that. But maybe that might also not be efficient, given that Facebook has quite a lot of data. So we might have to think of other ways to handle this case. So I hope you kind of like got the idea of like what these fuzzy matching and Levinstein distance metrics do. That's what they do. So there's another distance that we're gonna try to understand, which is Jaco and Jaro-Winkel similarity. So how does this one work? So I'm just gonna scroll down. Sorry about that. So it's also a similarity match between two sentences. So we can think of this as M. It denotes the number of matching characters, and we can think of this as one and S1 and S2 as like their real name and nickname, and this denotes the length of the first real name and the second nickname. So that's like the length of these two. Then the T here is the number of transpositions. So it's calculated as the number of matching characters divided by 2. So these elements refers to, and this is how you calculate the gyro similarity between the two strings. Okay, so you can also use it. It's also OMN. So yeah, M denoting to the real name and denoting to the nickname. But the point, guys, is that the reason I talk about these algorithms was just to say, let's get our data to be accurate. And some of you might be like, yeah, but these algorithms looks like they can actually do the work. Why do we still need to train a neural network? Right? I mean, if they can literally match, for example, Peter to Pete, right, with probably 96 accuracy, why do we then need a neural network? So I want to show you why we still need a neural network. Let's go to this. So these are actually nicknames that I found online, and we can look at them and they're quite accurate. For example, we have Penny, Penelope, we have Rob, Robbie, Ron, Aaron, Ronald. But the problem is that sometimes we might find that some of these are not as accurate as we might think. Let's take, for example, Ted, and we're just going to go here. We're going to take Ted and Theodore, and we'll see. You see, we're getting 86, and here these are actually this is a real name and a nickname. So you might think actually they were supposed to be matching. So sometimes the tone also matters a lot, and we're gonna see how we can use techniques to understand the tone. Like, you know how you pronounce a word, it might not write the same, but when you pronounce it, it's a nickname and they sound the same, right? You know what I'm saying, right? But we're gonna see how we use these techniques. But the most important thing, it's efficiency. So we don't want to come up with like these cool techniques, but then we kind of like forget about the efficiency. So but anyway, that's that. I want us now to look at, like, now we kind of like have label data, but we might want human label data, especially if we have nicknames like Ted and Theodore, and those are the nicknames whereby these algorithm, like in computer science, they might not actually be able to capture. So we can use something called active learning. Just to zoom in here, and I'm just gonna scroll down. So let's just zoom in here. So you can think of active learning as it's more like is a human in the loop framework for iteratively building a training set and models, right? So the goal here is essentially to choose informative examples to label, therefore decreasing the incorrect labels that we have. So what happened is that you can think of it like we train a model, a classifier, but we train a model on the label data. Then we use the classifier to be able to know which of the label data we are not good at. Then we try to send those labels that we're not good at to the human to be able to label them, or maybe they can get more data so that our model can be good. Something along those lines. So from an architectural perspective is that we have so we have like input label data. It goes into this label. Then we have trained, we have a model, we have a prediction, metadata. We push this along with the unlabeled data. Then we can see which of the data that we're not going good at, and we rank some of these samples that we're not good at, Then after we have ranked them, we enable the human labeler to label them. So we iteratively do so until we get an accurate model. So one could say, okay, we can maybe have multiple models. Then each model, like if we have multiple models and they can all agree on like the same thing, that okay, we can use something like that, but also that can be computationally expensive. So that's why we might want to use a technique called conditional distribution, whereby our classifier output some sort of like a probability, right? And we use that to know which labels we are not good at. For instance, if like one label we can be able to separate it from the other label, that's fine. Then if the another one is close to the decision boundary, then that's not good. Maybe we might send this to the labeler to label it, right? But the key takeaway with active learning for you to take in is that essentially is this technique whereby we have a human in the loop and we continuously learn by training the label that we have labeled. Then we use the unlabeled data along with the prediction metadata to know like which labels we're still not good at. Then we rank those ones that we're not good at. We then send them to the human. Then the human try to maybe do some data implementation, collect more data until the model is quite good at that point. But that's how we do it. I'll try to if you check out my second video, I did a data labeling. I'm getting into too much detail into these techniques using Snowkel, I think, to explain these concepts. Anyway, this is interesting. I love this part, guys. Dear feature engineering, because I feel like feature engineering is whereby we come up with like more assumptions and creativity to think of like things that could help us, our model, to be able to map real names to nicknames. So the first one that I'm going to think of is that we can take similarity features. So we don't have to discard all of those scores that we got from Leven's distance, Jaco, Wengler scores, and the frequency. We can still use those, right, as features into our model. We can use a country. I tend to believe that certain countries, probably maybe Robert is called maybe Rob in USA, maybe in South Africa is called something else, right? So maybe we can leverage country to assume that names are based on languages or something like that. So like I said, when I come up with features, it's always based on assumptions. I'm making assumptions. So yeah, I'm assuming that each country is going to have different names and something like that. I'm also making assumptions that gender is, we're gonna always have like different names between genders. For males and male, their name are going to be different. Hence, here I'm gonna include gender as a feature, and this might actually help our model to make predictions. So, like I said, that we can use something like SoundX. So essentially, it's an algorithm that takes two words and it tries to output a similarity score based on the sound. For example, there's certain words that sound the same, right? But when you write them down, they don't necessarily write the same, right? So this is an algorithm that we can use to essentially be able to know if like these names sound the same. I tend to believe that there are certain names, nickname and real name might sound the same, but when you write them might not sound the same. So hence here, I think this is a good component that we might add into our model to take help. So for instance, in South Africa, we have a nickname called KB, and some people call them KB. These are pretty much sound the same, KB, KB, but you write them differently, and now this score SoundX is going to give us a high score, and it's actually a nickname. So that's why it's something that we can add. Affinity, you can go about this, but one thing about like adding such features such as affinity, you might discriminate against other people. For example, maybe let's say the data is not distributed equally. Maybe like 3% is black of the names, 60% of the names is white, 20% of the names is Chinese. Then what will end up happening is that if you give something like Rob, it might always produce like maybe Chinese name, for instance, right? And maybe the model might be little biased. So I tend to also stay away from using features like this. Especially if we're gonna deploy this into a real world system. We're gonna look at the modeling part and see how it works. So we're looking at the modeling portion now. So we can think of like we're given a nickname, right? You can think we have a black box here, and the output, the goal is that okay, we want to have a set of real names, right? So this is a multi-label prediction. So one model that we can look at is XGBoost, which is very good at heterogeneous features like we identified in the feature engineering. This included country, age, maybe all of those features. However, homogeneous features like text, especially we tend to rely more on NLP or deep learning models, which I think they excel at these type of features, right? Because also you must think that we have like millions of names, right? Like there's so many names out there. So this could lead to XGBoost to overfit because we have high cardinality. So remember that we have like a set of names, like like we have like Robert. The second row is gonna be a second different thing. So the model can have a higher cardinality and can lead to XGBoost overfitting on some of these models. Okay. So another thing is that these models, XGBoost is gonna limit us in terms of the labels that we can have. So, for instance, if we take a look at, you need to specify. For example, let me scroll in now. So you need to specify the number of labels that you are predicting for, right? So, but like we said, the problems that map a real name, maybe a nickname, to multiple names. Maybe we don't want to limit it to a set of maybe 3 or 2, right? We want all the names that might be, all the real names that might be associated with that nickname. So another thing is that we need to encode our names with one-hot encoding, and XGBoost can suffer from sparsity because there's so many names. And if you're going to apply like techniques like one-hot encoding, it's going to really affect our model to actually do well. Okay, so one way we can look at a technique is called, multi-layer perceptron, whereby we going to embed our names with bigram and like bag of weights. So the point here is that if we're given a word like Michael, right? We're given a word like Michael. We have a vocab of characters like A, up to Z. Then we have 1, 2. Then what we do is that if we push M, we get all of their indexes, and we push all of those indexes to the embedding so that we can get embedding of each character. Then we can pass this to our model. Then our model is going to make a set of predictions across the whole entire names that we have. So for instance, with Hector, Peter, Mike, Liz, then it's going to give a high probability. For example, Mike here we can see 0.4. So here it's Michael. Maybe we have me or something like that. Maybe 0.2. But you get the point. But imagine, like I said, here we have like millions of names. Also, this might not seem quite efficient because you're trying to like your labels here are quite a lot, right? So one way maybe someone can say, okay, how about that we try to pass the name, the real name and the nickname together to our model. Then what we do is that we get the probability of, if this is, it's a binary classification. It's like are these two names nickname, right? Yes, if they are, we get a high score. Then this is much better because now we reduce the prediction to this. But then the question that I'm going to ask you is that the question said that given a nickname, given a nickname, we want all their real names. So we want a set. So the problem with this is that if we always have to have two nickname and real name and nickname so that we can get a product if they are close or not. So I don't know, but I don't think this might scale well, especially in production. Let's say if you have something like nickname, right, and you wanna get all the real name from this nickname. So this model will always rely on having two input like real name and nickname. So that's the downside of it, but it does help us to kind of like reduce. So how can we try to come up with something better then? So we can definitely train a multi-layer perceptron, whereby what we do is that we take all of the real names and we embed them. We take all of the engineered features like country, all of this, and we concatenate these. Then we push them into multi-layer perceptron. We get a prediction, a set of nicknames, right? That's how I think we can go about it. But it's still a lot of things that are still missing inside here. How can we definitely improve this, right? So we said we're going to use bag of words, but these can suffer from retaining the order of the characters in text, right? And what we can do is that we can probably use something like LSTM, right, which can help us to maintain that order for us because it's a sequential language model. So we can have that, and we can still have our embedding layer, and we can have a linear model until then we can have a dropout and softmax. So one way you can think about this is that the embedding layer is going to be quite intense. However, I was thinking of, because we said on the embedding layer we're gonna use the character level embedding, but the character level embedding can sometimes like not capture like quite meaningful embedding. So I'm thinking that we can tokenize, then we use the subwords and we use the byte pair encoding algorithm, which is to say that we can, I think this algorithm can help us to capture more meaningful embedding. We definitely know that we can't use word to vec because these are more like names. It's not like we trying to like embed characters or something like that. But maybe we can, but I'm just thinking from a character perspective. So we can train an LSTM after we have trained our subwords. The second optimizations that we can do is that we can have a dense layer after the LSTM to decodes the LSTM outputs. So that's another thing that we can do. Like I said, the character-based tokenization. Let me just do this. Essentially, we split the names into characters, reducing the embedding space and vocab. That's the advantage of using character level, right? Another advantage is that they can be able to manage misspelled names, right? But like I said, they can be less meaningful. And they cannot capture like quite complex interaction between like some of the words. So the advantage of me choosing to use swap words is that essentially this algorithm by pair, we try to break down the words into smaller units called word pieces. So you can think of William, we're gonna like be will, and IN or something like that. Now, into improving our model. So one way we can improve our model is that we know that back of words suffer from retaining the order of the characters in the text or names, right? So I've rather introduced an LSTM model, which is going to help us to retain the context between the characters, and and it's going to make sure that it's retained the order between the characters. So I've also included the dense layer, which is going to capture like the complex interaction between the characters and also the engineered features. We also have a dropout and a softmax. So now diving deeper into like some of the improvement, I have also included a character level tokenization. So we can think of this as like we split characters, the names into characters. So this actually enables us. The advantage is that it actually reduces the embedding space. So because now our vocab is going to range from A up to Z. So, however, even though it does help us to handle like misspelled names and stuff like that, it can be less meaningful. And another thing is that the weight tokenization, right? It suffer from less vocab. So we are caught up in these two, the disadvantage of weight tokenization and character tokenization. So because of this, I've decided to go with the sub-word tokenization. So you can think of a sub-word tokenization as like we break down the word into small pieces called word pieces, right? So you can think like we have a name like William and we break it down into W-I-L-L and I-N and I-N. So this is where each subtoken is a common sub-word that occur common in the language. So it uses this algorithm called a byte pair encoding. So a byte pair encoding is just a compression algorithm. So what it does is that it's a compression algorithm in which most common pair of consecutive bytes of the data is replaced by the byte that does not occur in the data. So by that, I mean like imagine you are given this text. And you have AA, B, D, ZZ. So we see that, okay, these are common words that occur. We're going to replace them with something that does not occur in the text. So which is Z. So we replace them with Z, Z. Does that make sense? So that's what we use. So how will the workflow now look like for taking the embedding data, pushing them into LSTM? That was the tokenization part. So this is how it will look like. We take the name, we tokenize it using the subwords byte pair encoding. We use word2vec. Yes, some of you might be surprised. Why word2vec? Isn't like that's supposed to be on the word? We're using it on the word. We can also use it on the subwords because remember that we have like Li and William, like we showed you, right? We can use it like that. So essentially the goal is to learn the numeric representation of the subwords, right? And we can use skipgram and cbow. Some people, they said skipgram is performed better in some, so we can try both of them and see how they work in as we're experimenting. We're gonna embed this and we push them into our LSTM model, right? That's like what we're gonna do, and that's like the whole entire architecture, guys. But what are some of the techniques that we could have leveraged, which I think could still work? One of the techniques is a seamless network with the triple-S loss. So essentially you can think of this as we try to map all the names that are, we will try to map all the nicknames and name on the same space, and we'll try to push all the names and nicknames which are not related far away, right? So that's what we'll try to do. I think also this might have worked, especially if we're trying to deal with names and nicknames that don't have a pattern. So I'll definitely try to use a seamless network with a triple-S loss. I didn't use the sentence bed, like I didn't want to touch transformers because I was more concerned on the character level, and sentence bed might be quite expensive in production. Not only that, it captures context very well, especially when you're dealing with weight sentences. I think that's why they're calling it sentence bed, right? I wish I could have spoken about conversion matrix, but I think also because maybe if we're working on a classification, if this was a classification project or something like that, I would have actually spent it on that. Yeah, that's the system design, guys, I have for this. Yeah, I'll keep on creating this. If you like them, let me know. And yeah, if you don't like something, let me know so that I can improve. I really appreciate you guys watching to the end. Thanks. Bye.